All right, we are now moving on to discuss a new topic, which is going to seem like an old topic. We are going to talk about gravity. Um, and so when we were in the force chapter, we discussed the uh, gravitational force on an object near the surface of the Earth, and we called that force the weight, and the magnitude of that force is m, the mass of the object, multiplied by little g, which near the surface of the Earth is 9.8 meter per second squared, right? And you sort of would picture the situation like this. You've got the ground and you've got maybe a ball nearby, and so that force of gravity is just what we call the weight. Now, what we want to do in this chapter is take a step back and think more generally about the force that exists between two objects with mass that are a certain distance apart. And so this introduces the universal law of gravitation, and this is going to allow us to talk about the force of attraction that exists between any two objects in the universe that have mass. So this force is equal in magnitude to g m1 m2 over r12 squared. So let's go through what all of these terms refer to. First off, this is the force between two objects with mass. So m1 and m2 here are the two objects with mass. You can look at my picture over here. There's m1 and m2. r12 is the separation between the two objects, and it's really the separation between the center of mass of the two objects. So my m1 here is just a uniform mass, so the center of mass is there. My m2 is uniform, so the center of mass is there. So it's the distance between the center of masses of the two objects. So the force that exists between these two objects depends on the product of the two masses, and then it also depends inversely on the square of the distance between the two objects. And then this last term, g, this is known as the universal gravitational constant. That's a constant equal to 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. So this right here is the more general expression for determining the force of gravity on an object due to the fact that there's another massive object nearby. And so I've highlighted this here. Apparently, what happens when you're near the surface of the Earth is that when you plug in m1 is the mass of the Earth and r12 is the radius of the Earth, that when you plug in all those numbers, what must happen is that this term here, which is just g, mass of the Earth, divided by the radius of the Earth squared, when you plug in all of those values, so here I've done so over here, plug in all those values, you end up getting 9.8 meter per second squared for everything here in this parenthesis. And so that tells you that, all right, the force due to gravity on an object, any massive object near the surface of the Earth, is just mg. And so this is why we were using mg, which we were calling the weight, in the force chapters, because most all of our problems in that chapter and in most of this course are objects that have mass are placed near or on the surface of the Earth, and so that force due to gravity is always just represented as the mass of the object multiplied by little g. Now, little g comes from the fact that the universal gravitational constant g multiplied by the mass of the Earth divided by the radius of the Earth squared. Right? That's where little g comes from. Now, this is also why if you were on a different planet or different object, like if you were on the moon, that's why little g works out to be smaller on the moon, because the mass is different and the radius of the moon is different. And when you plug in those values, you end up getting about 1/6 of the acceleration due to gravity near the surface of the Earth. So another question you can ask is, rather than being near the surface of the Earth, where the force is just going to be m times little g, 9.8 meter per second squared, what happens if you aren't close to the surface of the Earth? Now g will have a different value. You'll still have g in the calculation, you'll still have the mass of the Earth, but now r, how far away you are from the center of the Earth, will not be the radius of the Earth, it'll be some larger value. And so as you get further and further away from the surface of the Earth, r is getting bigger and bigger and bigger. Well, r is in the denominator, and so that means the acceleration due to gravity is going to be getting smaller and smaller and smaller. Now, one way that we characterize or describe the way that this gravitational effect changes as you get further away from a massive object is something known as a field. So there's a way to describe gravity in terms of a field, and the way you want to think about it is that if you place an object with mass at a certain location, what gravitational force will that object experience? And so the gravitational field is a way to essentially predict what's going to happen if you place a mass at this location. And so what you need nearby is you need another massive object that essentially is producing the gravitational field. And so I can take this expression up here and I can just rewrite it sort of in vector form. And now this is for any massive object m. The gravitational field, we might call it little g, would be the universal gravitational constant multiplied by the mass of the object and then divided by r squared, how far away you are from that object. And this would describe something known as gravitational field. In the units we're typically using, the units would be meter per second squared, right? It would correspond to an acceleration. But a slightly more useful unit, which is equivalent, is a Newton per kilogram. And then if you use this unit to think about the field, then it immediately becomes obvious that the field is a way to describe if you place a mass at that location, you'll get a certain force. Because basically you're just going to take your field and multiply it by a mass value, and when you multiply by that mass value, the kilograms will cancel, and you'll get a Newton's worth of force on the object that you've placed at that location. Now, the field here depends on the mass of the object, m, and how far away you are, r. The field does not depend on what mass you place in the field, right? The mass only depends on, like if we're talking about the gravitational field of the Earth, the mass only depends on, or the field only depends on the mass of the Earth and how far away you are from the Earth. Now, fields are going to play a really big role in 102 as we begin to think about electricity and magnetism. And the reason why they play such an important role in 102 is that we don't have a similar analog to gravity in 102 with respect to electricity or magnetism forces. In 101, almost all of our problems include the Earth as one of the masses in this expression up here. Right? One of the masses is almost always the mass of the Earth. Well, in 102, when we're looking at Coulomb's law, which depends on, functionally it looks exactly the same, but it depends on the charge of the objects and the separation. And we don't have a standard charge that we'll be placing other charges near. And so we actually need to use the field approach to better conceptualize and better understand what's happening in 102. And now that we have a new functional form, a new representation for the gravitational force, we can revisit gravitational potential energy. Remember what the definition for potential energy is. We're evaluating a force over some path length, right? We're integrating. And so now we're just using a different functional form. We're using the universal law of gravitation. And so just plugging in that functional form, we end up getting this expression when we evaluate this integral, 1 over r squared. Oh, I forgot the, looks like I forgot a dr in there. But when we integrate with respect to dr, we end up getting this function, or this result. And so you can see that there's G, mass of the Earth, so this is gravitational potential energy, right, near the surface of the Earth, mass of the Earth, mass of the object, and then 1 over r. And so the functional form then for the potential energy of a massive object near the Earth is this expression right here. And so I've got this picture where here I'm not talking about the Earth, but just any object of mass m, and you take another mass and you move it from R1 to R2. How does the energy, the total energy, change? Well, the total amount won't change, but the amount in each type of energy might change. So initially, at 1, you would have a kinetic energy term, and then a gravitational potential energy term. And then at 2, you'd have a kinetic energy term and a gravitational potential energy term. Now, we can ask some specific questions related to sort of real-world applications or real-world effects. What if we wanted to launch an object, say, off of the surface of the Earth or the surface of our massive object? What if we launched it, and what are the requirements for the object to actually escape? That is, to never fall back down, right? You may have heard the expression, what goes up must come back down. Well, that's actually not true, right? If you provide a large enough initial speed, then the object can actually escape the host object or the host planet. And so the minimum speed required would get the object all the way out to infinity, so infinitely far away, and at that moment have essentially 0 speed. If it gets launched any faster than the minimum speed, then when it gets out to r equals infinity, it'll still be moving, right? And so that's why that would correspond to the minimum speed. So let's just go back to the conservation of energy expression. So 1/2 mv1 squared, and I want to launch this thing from the surface of my object. So the potential energy term, R1, is the radius of the object, of the planet, if you will. And then for state 2, I've got 1/2 mv2 squared. Well, v2 is 0, so 1/2 mv0 or m0 squared. And then R2, that's where we're at that state, is we're infinitely far away, so I've plugged in infinity there, or 1 over a very large number. And so these two things are both 0. So that means these two terms on the left have to equal 0, and so I can move this term over to the right. And then I can solve for v1, and so the speed that's needed for this object to escape, and that's why I rewrite this as v escape, so the escape velocity is the square root of 2gm over r. So it depends, the escape velocity just depends on how massive the object is you're being launched from, but also r, the radial extent, right? How far from the center are you starting? And so as m goes up and or r goes down, so the more and more massive the object is, the smaller and smaller in radial extent the object is, the escape velocity goes up. That is, you need to launch the object with a larger and larger initial speed for it to leave. And so one really interesting result of all of this is that you can have scenarios where the object is so massive, or the radius is so small, or some combination. Really just think of the density. The density of the object is so great that the escape velocity will actually need to be greater than the speed of light. And this is a really interesting artifact of the math and of gravity here, but that essentially leads us to the idea of black holes. That is, there are objects that are so dense, that is, such a large mass in such a small volume, that objects would have to be moving faster than the speed of light to escape essentially the gravitational pull of the object. And so things will never leave. And that includes light. And so that's where this term black hole actually comes from, is that the escape velocity to leave the gravitational pull of this really dense object, the speed is greater than the speed of light, and so nothing can escape.